Hi, my name is Sloan Smith, and this is Experiment 3, Circuits for Physics 2212. The purpose was to predict and observe ohmic resistors and capacitors in our circuit. The principles we used were Ohm's law, the loop rule, and the node rules. As a result, we observed ideal circuit behavior and were able to compare the ideal behavior to the predictions of the principles. Finally, we found agreements in the theoretical time constant and the observed time constant. For this experiment, the system was our circuit, and the surroundings was the rest of the world, which did not interact. We used an online simulator to make circuits with ideal resistors and capacitors. For the first part of this experiment, we set up the circuit shown in the picture. The current around this circuit was both computed by the computer and calculated to be 0.02 amps. The ammeter in this also read 0.02 amps when it was inserted backwards. When a voltmeter was used to connect the circuit, the current did not flow, resulting in 0 amps of current and a reading of 3 volts on the voltmeter due to a potential difference. Finally, for the entire round trip when the circuit was connected, it was 0 volts for this circuit. The picture shows a graph of voltage across each component of the circuit. The voltage increases extremely quickly in the EMF batteries and decreases across each of the resistors, resulting back in the 0 it started as. When connecting an ammeter in parallel to the circuit, the current increased around the entire circuit because it was able to flow around a 100 ohm resistor. The calculated resistances of each part of the circuit was 48 ohms for the resistor that was set at 47, and 102 ohms for the resistor set at 100 ohms. The resistance calculated of the wire and ammeter were both 0 ohms. For the second part of the experiment, we observed current decreasing as a capacitor charged and discharged in a resistor-capacitor circuit shown to the right. It holds both a light bulb which has resistance and a 0.2 farad capacitor. The charge time for the light bulb at 10 ohms for the capacitor was 15.4 seconds, and its discharge time was 18.8 seconds. When the light bulb was increased to 20 ohms of resistance, the charge time was 30.3 seconds, and the discharge time was 36.1 seconds. To find the time constant, we can take measurements of the voltage across the capacitor at multiple instances of time. When we plot this, we can find the time constant. The way this was done was, we took a measurement of the voltage across the capacitor every second for 20 seconds. Then, using the voltage of the batteries as the delta V naught, we plotted the natural log of delta V divided by delta V naught against t. This gave us a line of best fit, and the slope of this line of best fit, according to the theoretical relationship, would be -1 over RC. From the line of best fit, we can find the RC value. For our light bulb, which had a resistance of 30 ohms and a capacitance through the capacitor of 0.2 farads, the ideal time constant was 6. According to our relationship, therefore, the slope of the line should be -1/6 or -0.1167. The slope of the line we found was -1.67, which is extremely close to -1/6. The sources of error that could cause the slight change is that the data was taken every second. For more accuracy of data, we could have taken closer time intervals, such as every half second. What if this experiment was done in real life and an actual ammeter was used instead of an ideal one? What would be different about this real ammeter, and how would it have affected the circuits I hooked it up to? The response is that a real ammeter would have some resistance, which would decrease the measured currents, changing them from the ideal values we got. What if we were doing this experiment in real life and used a real battery to charge a real capacitor? How quickly would it charge? Would this prediction happen in real life? A capacitor with no resistance would theoretically charge instantly. However, since batteries and wires have some tiny resistance in real life, this charging would happen in nanoseconds. Thank you.